Hi, and welcome to the next edition of the Blood Bank Guy video podcast. This will be the first part of a two-part podcast. In this section, we'll be discussing an introduction to the transfusion-transmitted diseases. In part 1B, which will be recorded later on, we'll be doing the specific transfusion-transmitted diseases. Just to let you know, this is being recorded in September 2011, so as always, I've made things as up-to-date as I possibly can as of right now, but please check to make sure that everything is still up to date if you're listening to this down the line. Also, you can download a copy of the handout for this presentation at www.bbguy.org. Just follow the podcast symbol to podcast number 3. Anyway, so as I said, we'll talk a little bit about general philosophy and basic screening tests today, a little bit on terminology at the end, and then we'll cruise on the next time to do the specific organisms. In order to discuss these transfusion-transmitted diseases, I thought that I would give you a little bit of a story that just kind of illustrates how we can see transfusion-transmitted diseases today. We get the impression that they don't happen very often. The truth is that they don't, but the bad news is that when they do happen, they cause great consternation. Just an illustration from my personal experience, last October 22, 2010, was pretty much a standard day at the blood center where I work. It was casual Friday, so everybody was relaxed, no big deal, and then all of a sudden we got a bomb dropped on us, and that bomb was a report in the Morbidity and Mortality Weekly Report describing a case of HIV transmission through transfusion in Colorado. The patient was in Colorado, the donor was in Missouri. It was a very alarming situation. It became evident fairly quickly, from my perspective, thank goodness, that the donor was not associated with the blood center where I work. Not that it made me feel a lot better, because the patient who got the HIV through transfusion was actually at one of the hospitals which we serve. Anyway, this particular individual, this particular donor, had donated in a high-risk period and had transmitted HIV to a particular recipient in Colorado. As you can imagine, things hit the fan very quickly. The Denver Post picked up this story pronto that morning, and you can see it was this story was posted at a little after 10 a.m. When on the day that the MMWR came out. I found myself talking to the Denver Post, I found myself talking to one of the local news stations, and then all of the local news stations before long. I don't know if you can see this on this particular story. About halfway down, you get the really great quote from me. "I was horrified," Dr. Joe Chaffin said. Yeah, that's an awesome quote, isn't it? And sadly, before too long, I found myself not only being quoted on the internet, but actually appearing on TV. And there's a nice shot and another really great shot from a different channel. I obviously translate very well to TV. Or not. And before long, it became very evident that I was becoming the face of this, even though, as I said, I wasn't even involved. And to the extent that my boss very quickly was asking, can we make him be quiet? We don't want to hear from him anymore. Well, what went wrong in this situation? It was pretty clear in retrospect what had happened. The donor had lied about high-risk sexual activity with both males and females, and he was tested during a window period. Basically, he had a very early HIV infection that had not become evident yet through laboratory testing, and as a result, passed on HIV. Well, that story is obviously sobering and concerning. Thankfully, though, we can point to some very substantial evidence that we are getting much better with getting rid of transfusion-transmitted diseases. This is the chart that just looks at post-transfusion hepatitis from 1969, when 25% of patients who got transfusions got post-transfusion hepatitis, all the way up till now, or close to now anyway, when that risk is very, very close to zero. You can also see some of the other infectious disease tests that have been implemented during that time frame, and we'll talk some about those as we go along. The basic idea is pretty simple. We have a donor on one side, we have a patient on the other side, and we're trying to keep that donor from spreading a potential infection to a patient. The way that we do that is fairly simple. We have three main cogs, or three main bricks in the wall that we're trying to build. And those bricks, from the donor center perspective, are education and self-deferral, screening questions, obviously designed to screen donors out, and donor testing, finally. All those things work fairly well, but obviously, as you saw in the example that I just told you about, occasionally things can slip through. We obviously try to prevent that. The FDA looks at things in a slightly different way. They have what they call the FDA's 5 layers of safety, and you can see them bouncing down on the screen right now. They include some of the same things that we've already talked about, but the last two is what I would call your attention to. The FDA requires us to quarantine the units of blood until everything is done, until everything is clear and that unit of blood is truly ready to be released from the blood center. Also, the FDA requires us to operate under the good manufacturing practices, or the quality practices that are prevalent in the pharmaceutical industry, but also blood centers and blood banks, transfusion services, are required to operate under those same principles. Now, as you can see from our examples, sometimes these things don't work, and it brings us to what is kind of the next step. It's not yet available. This is not yet available in the United States, but the big wall that comes between the donor and the patient, we're hoping will be pathogen reduction or pathogen inactivation. Pathogen reduction is fairly simple in concept, but it is proving a little bit more difficult in terms of getting it approved in the United States. It's basically direct treatment of the blood product to eliminate or to at least reduce substantially infectious organisms. There are a lot of ways that you can do this. Traditionally, this has been done with heat and solvent detergent treatment to eliminate enveloped viruses, for example, methylene blue treatment. All of those things are possibilities. But what we're looking at in the United States right now is to try and get the approval for direct nucleic acid manipulation. In Europe, you're already able to do that, but you're not yet able to do it in the United States. And let me show you what I mean by that. This is just one example of the two main systems which are competing to try and be approved first in the United States. This happens to be the Intercept system, which is from Cirrus, and the competing technology is Mirasol from Caridian BCT. But they're basically the same general concept. Essentially, as you see on the left side of the figure, a substance is introduced into the blood product which has a very specific binding affinity to nucleic acid. In the case of Intercept, it's a molecule called amotosylin, and it's riboflavin in the Mirasol system. So anyway, this substance goes in, it binds to DNA. It's a reversible binding, no big deal. But when ultraviolet light illuminates that substance, then you get permanent cross-linking and permanent binding of the nucleic acid, which keeps the nucleic acid from replicating and basically renders, if this is an organism, it renders the organism incapable of replicating. Interestingly, it also renders white blood cells, or anything with nucleic acid incapable of replicating. And so that brings us to some of the applications for pathogen reduction. Obviously, we're looking for it to deactivate infectious organisms, such as viruses and bacteria. It also probably will do the same thing for parasites. Interestingly, it will also, as I mentioned, do a similar thing for white blood cells. So transfused white blood cells are the cause of significant numbers of problems for us, and it's one of the reasons that we leukocyte reduce in the United States and really around the world on an almost universal basis. Anyway, with that white cell deactivation, you could end up with a decreased need to irradiate because transfusion-associated graft versus host disease is associated with transfused white cells. You could eliminate the need or decrease the need to leukocyte reduce, and potentially to culture blood products such as culturing platelets prior to their release. Anyway, so the disadvantages, of course, to pathogen reduction is just A, that it's not available in the United States, and B, another potential disadvantage is that the technology is not quite worked out for whole blood or red blood cells yet, but that is coming down the line. Okay, well, let's move on and shift gears and talk a little bit about the test methods that we use to test for infectious diseases. As I said, this is just intended to be a general overview. This is not, by any stretch of the imagination, designed to be a specific, detailed look at each of these testing methods, but I want to make sure you have a general feel for them before we go in the next section into the specific organisms. So let's start with ELISA, or EIA, enzyme-linked immunoassay. EIA and ELISA are the same thing. Basically, EIA was developed in the 1970s. It's the majority of the testing, the screening testing that we do in blood banks nowadays. It is the vast majority of antibody testing, as well as some of the antigen testing specifically for hepatitis B surface antigen. You should be aware that EIA is a great test. The technology is wonderful. It's very, very sensitive. It's very, very specific. And with that being said, it would make you wonder, why would we ever get false positives with EIA if the test is very, very specific? Well, the problem, of course, is that when you're dealing with a population that has a very low incidence of disease, as with blood donors, because blood donors have been self-selected as well as selected through our screening technology, they're expected to have a very low frequency of disease. So any positive test that happens is almost by definition, despite the fact that the test is specific, the majority of tests that we get that turn out positive are actually false positives. What we're obviously trying to do is to try and eliminate the false negatives as much as we can. All right, let's look at EIA for a second. This is one of the testing methods that we use. Obviously, EIA is done on several different pieces of equipment. The piece of equipment that you see on the left there is an Ortho Summit processor. And basically within little micro wells, we do some specific things. I'm going to show you the way that we test looking for an antibody. So if you're looking for an antibody, in your test kit, you bind antigens, or the manufacturer binds antigens to the base of one of these little microwells. To that, you add your sample, which may or may not contain an antibody against that particular antigen. In this case, I'm showing you a positive test, so it does contain the antibody. Add in the sample, and the antibody goes and binds onto those antigens. Well, unfortunately, you can't see that, so you need an additional step. In fact, we need a couple of additional steps. The first thing that we do is we actually add in an anti-human antibody. This antibody is designed to bind to those previously bound antibodies, and they are also tied to an enzyme. Remember, this is enzyme-linked immunosorbent assay. So that enzyme bounds to the anti-human globulin. You'll see that kind of complex. Unfortunately, again, you can't visualize that, so you need an indicator. You need a chromogen. That chromogen goes, the enzyme catalyzes a visible color change, and you can detect that change in color through the test apparatus. Now, chemiluminescence, or CHLIA, is a very, very similar process. The difference really is mainly in how the detection methods occur. In other words, with EIA, you have color change. With chemiluminescence, you have generation of light from a chemical reaction. The principle is very similar. As I said, it's just the detection method that's different. A substance called acridinium, when exposed to hydrogen peroxide, will give off visible light. The main instrument that's used to do chemiluminescence is the Abbott Prism system, and it does the test that you see there on the screen. And chemiluminescence really is just like a glow stick. If you think about the glow sticks that kids crack and they give that bright green light, that's really a chemiluminescent reaction. Again, hydrogen peroxide exposed to a particular substance gives off that glowing light. And there's a picture, by the way, of the Abbott Prism on the bottom of the screen. From this point forward, just so you know, anytime I say EIA, I also am meaning EIA or chemiluminescence. I just don't want to keep saying that over and over. Now, with that being said, let's move on and talk about Western blot. Western blot is used in our blood bank testing for one specific reason, and that's for confirmation of reactive EIAs for HIV, specifically for anti-HIV. It's very similar, the Western blot is, to EIA in principle. The difference is the proteins are actually separated onto a membrane by electrophoresis. So they separate out, then we add our sample, the antibody, if it's there, binds, and again, we needed some sort of detection method. The issue with Western blots, and the big problem with Western blots, is the relatively high number of indeterminate samples that you get, indeterminate results you get, I should say. So basically you have three possible results from Western blot. Either it's positive, which helps you and confirms the EIA result. It's negative, which again helps you. It puts the donor into a different category. But the indeterminate category is always difficult to explain to donors. Well, you're not positive, but you're not negative, and it makes for difficult conversations. Realistically, those with indeterminates should not be considered positive, but as I said, it's difficult to explain. So for that reason, we've come up with some alternatives to Western blot, and I'll show you that in just a second. But first, let's look at Western blot. I've drawn arrows to show you the most important bands in a Western blot, the GP 160 and 120, GP 41 and P24. Those are the bands that, if present, will define whether or not someone is positive on a Western blot. And those bands correlate to specific proteins and glycoproteins in HIV. Okay, so as I said, Western blot, the big deal is indeterminate samples. So one of the alternatives, in fact, the main approved alternative to Western blot for confirmation is IFA, or Immunofluorescent Assay. It's again used for HIV confirmation. It's equivalent in terms of a positive result on an IFA confirms HIV, just like a positive result on Western blot confirms HIV. This is done on glass slides with antigens bound to T cells in wells on that glass slide. And again, it's the same sort of principle. The antibody binds. Our detection method in this case uses a fluorescent substance. And here's how that looks. Here's a positive IFA. And again, you can see that that has potential to be fairly easy to read, though I will admit that there is some art to it. You tend to get fewer indeterminate results with IFA than you did with Western blot. Now here's RIBA, or RIBA as some people call it, but it's recombinant immunoblot assay. RIBA is used specifically for HCV confirmation. In other words, you get a reactive anti-HCV on your Elisa or your EIA or your chemiluminescence, and you want to confirm that. You confirm that using the RIBA. RIBA is again similar to Western blot. Though electrophoresis is not necessarily used. You get recombinant antigens bound to a strip by the manufacturer. It's important to recognize that the current RIBA is required to have the same antigens present as the antigens present on the current version of the EIA. That's currently version 3.0. I said a lot of currents there, didn't I? It's 3.0 right now, and so the RIBA is RIBA 3.0, the EIA is EIA 3.0. Same principle once again. The antibodies bind, you need a detection method. In this case, it's a peroxidase-labeled anti-human antibody, and you add hydrogen peroxide and a chromogen, and you get visible change. And here's how a RIBA 3.0 looks. On the right side of this image is a RIBA 3.0, and it has the specific HCV antigens. Again, those are required to be the same antigens that are present on an EIA 3.0. All right, let's move on and talk about NAT, or nucleic acid testing. One of my pet peeves. I'm so sorry, drives me crazy. Don't say NAT testing. That would be nucleic acid testing. Don't do that. It's just NAT. When you look at NAT, there are two main variants that are approved for use in the United States. The first is just PCR, which is what everyone thinks about when they think about NAT. The second, though, is transcription-mediated amplification. We'll talk more about TMA in just a second. But first, with both PCR and TMA, you're basically using molecular techniques to find, amplify, and detect specific genetic material, and you detect it through amplification. NAT is very highly sensitive, and it is highly specific. And it's a great test. We use it extensively in blood banks nowadays. Interestingly, PCR itself was actually thought to be invented, or rumor has it, legend has it, that it was invented in 1983 when someone was driving along the Pacific Coast Highway, this beautiful stretch of road in California, and the dude just thought, let me come up with PCR. Okay. I don't think I would have done that, but good for him. Anyway, PCR is designed to amplify a selected genetic area. It has a very specific sequence, which I'm sure most of you have heard of. It includes denaturing and annealing and extension. It uses a thermocycler to change temperatures. And basically, you repeat that cycle over and over, and you get a chain reaction, which leaves you with a very large amplicon, or very large amplified area, target area of DNA. Here's an image of how that works. You have the 5' and the 3' ends of DNA, which separate as a result of heating generally. You bind primers to that area, to a specific target area, extend those single-stranded DNA single-stranded DNA fragments through DNA polymerase and then do it over and over and over again. So in the end, you end up with a large amplicon of DNA. Now TMA, on the other hand, transcription-mediated amplification, actually it looks at things slightly differently. It's faster, it's probably a little more sensitive than traditional PCR. It's theoretically simpler because everything is all contained within your reaction kit. You don't have to add stuff, subtract stuff. There's no thermocycler needed. Basically with TMA, you can use either an RNA or a DNA target, and you end up with an RNA amplicon rather than DNA. It's amazing how many copies the amplicon can have within an hour, up to 10 billion copies within an hour. And here's just an image of how TMA works. TMA is done on one specific platform. It's on the Novartis platform that we use in blood bank testing. And in this particular case, this image is showing you the use of TMA to amplify a ribosomal RNA target. That's actually a cool thing because ribosomal RNA tends to be more abundant than either regular messenger RNA or DNA within the nucleus, so it may be an easier thing to find. Again, you can follow through, but the short version of this, it's a similar concept. It's just that you use RNA polymerase, you go through a DNA-RNA hybrid, and you end up at the end, as I said, with an RNA amplicon. It's alternative technology, and it works really well. A couple other things on just speaking of terminology, a couple things that I wanted to make clear to you because these terms get confused by people a lot. The window period, the eclipse phase, and the incubation period. Window period and incubation period especially get confused. Eclipse phase is kind of a virologist term, but you'll hear it described sometimes, especially, well, in particular, in the case that I mentioned to you earlier, in the Morbidity and Mortality Weekly Report, they described this as an eclipse phase transmission. Okay, we can argue back and forth, but it's basically a window period for me. So window period is specifically defined as the period from infection all the way through the point at which you can detect the organism in the laboratory. Incubation period, on the other hand, is from a similar period, infection or exposure. Exposure may be a little earlier than infection by definition, but the incubation period goes to the time when clinical symptoms appear. That may be longer than the window period, it may be shorter than the window period, but in general it's fairly similar. The eclipse phase, on the other hand, to a virologist is the time from entry into the cell on the actual cellular level. Okay, you could define that as infection. I wouldn't argue with you on that, but it's until the time when you can actually look in a cell and see the presence of new virus. That again may or may not correlate to the presence or to actual lab detection. And let me show you how that looks, specifically looking at window period versus eclipse phase. So if you follow along from the time of exposure or infection or entry into the cell in the eclipse phase, you watch the blue line and it goes up and you have an infectious viral load by the time you get to the potentially infectious viral load by the time you get to the end of the eclipse phase. However, that may or may not correlate to the time where detectable antibody or antigen is present. You can see the window period ends with the purple line when the purple line gets to the point where you can detect the antibody in this case or an antigen. The infectious period is the time in between the end of the eclipse phase then and the end of the window period. And that's a very important distinction, and it's very important to understand that our goal is to decrease that as much as possible. All right, a couple of other things, actually just one more slide. The terms initially reactive and repeat reactive confuse people sometimes. Initially reactive simply refers to a situation where someone has a screening test, an EIA or chemiluminescence test, whose value exceeds the cutoff. So it is reactive by definition. Those cutoffs are established within the manufacturer's instructions in the test kit. Once you get an initially reactive test, that doesn't automatically mean that the donor is considered positive and the unit is thrown out. Again, according to the manufacturer's instructions, the next step would be to repeat that test in duplicate. So repeat it twice, okay? If one or both of those repeat tests is also reactive, that's when someone is called repeat reactive. If you're repeat reactive, your unit is always going to be discarded. We don't utilize those units, and the donor may be deferred depending on the organism that you're reactive for. So that's all I have to say about terminology. That's all I have to say with the introduction to this section. The next time we get together, we're going to talk a little bit about some specific organisms. We'll talk about all the organisms that we test for, as well as emerging infections in the future. Thanks very much. It's good to see you, and we'll talk to you again next time.